you can say that the expected number of false positives among the voxels that you report as significant is 0.01. I'm not going to go into how this is calculated in detail, but I will say that it adjusts itself to your data pretty well. It has a few kind of odd properties that are worth knowing about. One is that sometimes it produces no threshold at all. You say that you would like to report those voxels for which you can assure yourself of a false positive rate of 0.05, and the algorithm says we looked through all the p-values, and we were unable to come up with any such threshold. That's the outcome. I should mention that the FDR procedure operates on p-values. So as long as you have a big pile of p-values, you can calculate an FDR threshold. So that's one kind of odd consequence. The other odd consequence is that with typical family-wise error rate correction, if you set a threshold, a t threshold of 3.7 or whatever it is, and you're using the same kind of like Bonferroni correction or RFD correction, you tend to end up with kind of the same threshold, and things are comparable in the sense between separate analyses, in the sense that if something lights up here and not here, you know at least that it was numerically brighter. Now, you can argue about whether that's actually a helpful thing to be able to observe. Actually, on the whole, it's been harmful in imaging because people tend to over-interpret that kind of observation. But that aside, FDR makes even that kind of numerical observation invalid. FDR thresholds can show you more stuff, not because the actual voxel that suddenly is active has become brighter in this new analysis, but because some other voxel has become brighter. So if you have two analyses of the same data, and one of them changes some little detail, some facet of your independent measure that causes voxels way over here to suddenly light up, but doesn't really change the statistical relationship with voxels over here that much, the addition of all these massively significant voxels will tend to make the ones over here fare much better in relation to your threshold. So this is a sort of counterintuitive property of FDR that I think is worth knowing about, because it's very easy to run two FDR analyses and say, look, when we do this, this is more significant in the sense that it wasn't before and now it is. And in fact, as incorrect as that usually is, it's even worse in FDR. Those are the bad things about FDR. It sort of snuck its own little standard for statistical significance into the field, and it does a lot of sort of counterintuitive things that make interpreting it very tricky. The good thing is that it does actually allow you to say things about your data that would be that are justifiable and that would not be easy to say if you were using traditional family-wise error correction. So, for example, if you do an FDR analysis and say your FDR threshold, it's called the Q value, is 0.05, which some people I know think is unconscionable, but I don't think it's always unconscionable. All that means is that 5% of the voxels that you see in your analysis, on average, are going to be false positives. Well, that's not good, but if you have an enormous blob, and let's just pretend for a minute that that blob is filled with voxels that are all completely independent comparisons. If you have an enormous blob of thousands and thousands of voxels, and you don't really care that much about which ones in that blob are significant, and you don't have too many voxels outside that blob that could be accounting for the significant voxels, then you're pretty well justified in saying that there's some relationship inside that blob somewhere, even if you can't say exactly where, because you know that 5% of them maybe are false positives. So,
what about the side that you said? Let's assume for a minute that they're all independent, but we know they're not. So what?
Well, yeah. I mean, I guess you never expect complete independence. The data are always smooth, but as Peter mentioned before, a lot of times you have these identical voxels, right. And certainly in that case, I think. It could be argued that, it probably should be argued, somebody needs to think this through, that it should be 5% of the little blobs and not 5% of the voxels. But still, whatever the unit is, even if you decide that what you really need to do is something akin to what people do in fMRI and use something like recells or resels or however you pronounce it, some sort of measure of how big how big a sort of virtual voxel you would need in order to have relative independence. At some level, with FDR thresholding, you can assure yourself that you have enough stuff active that you don't have to worry too much about the 5% of the stuff that's not true. So I think that's actually very useful, and that's what I've used to justify to myself having my name on articles that use FDR. Justify, rationalize, whatever I call it.
Did you ever allow us to do that? Never.
0.05?
Yeah.
Well, that's because we got good results at 0.0.
Stamping your foot.
That's just because I was scared of Jared, but
Just one.
but we had good results at 0.01 and 0.02. So why push our luck? Why join that disreputable club?
Okay.
Um,
Now he's sounding more like Dan.
So the last method that I described here is just I don't know why I put these two on the same line, but just using the distinct voxels is just a way of looking at is a sort of a way of doing Bonferroni correction when you know something very specific about the non-independent, specifically the identical voxel thing. RFT, random field theory, or Gaussian random field theory, is what's often used in fMRI, and I don't think it really has much application in lesion analysis, especially because once you look at distinct voxels, you tend to get something that's as powerful as RFT would be. In fact, what we found through a lot of these simulations is that permutation testing can be more powerful than looking at distinct voxels, but it often isn't. So doing Bonferroni correction for distinct voxels actually turns out to be, in many cases, a solid winner for how to threshold VLSM analyses. Okay, so I see that it's 4:53, and I have approximately 17 hours worth of miscellaneous topics to discuss here. I guess maybe some of these we've discussed already, so I don't have to go into too much detail. And I think limitations of univariate methods, which is down here at the bottom, would literally be another 17 hours. So we can skip that. Are there any requests? Any topics here that look particularly exciting to anybody, or are we all tired?
Yeah, what about including the right hemisphere patients?
Yeah, so, this is a good short one because I don't have a ton to say about this, but people will ask me sometimes whether they should, when they have very discrete groups of right hemisphere versus left hemisphere patients, whether they should throw them in the same analysis or consider them separately. And it's a sort of weird little topic because on the one hand, it sounds like something very specific to right hemisphere, left hemisphere, because they tend to be discrete, especially if you're only including unilateral patients. So they tend to be well, exactly when you're including only unilateral patients, they tend to be separate. They'll be separate groups. I think what it comes down to is it's a sort of general example of making sure the statistical test you use is actually a test for what you're interested in. And when you include left hemisphere, and every time you do VLSM, what you're really doing is saying, I want to compare patients with damage right here to all the rest of the patients. So all the rest of the patients are in your control group. So if you include right hemisphere and left hemisphere patients, then to some extent, the effects you see could be hemispheric effects. Whereas if you just include left hemisphere, basically not a difference really between this voxel and other voxels, but it could be just a difference between right hemisphere and left hemisphere that happens to correlate really well with looking at just that voxel, because it's a left hemisphere voxel. Whereas if you just include left hemisphere effects, what you're seeing is that voxel versus the rest of the hemisphere. Now, there's nothing really that special about hemispheres, right? Suppose you're just looking at left hemisphere, and you look at that voxel and you get an effect. Well, that could be an effect of anterior versus posterior, not really an effect that's specific to that voxel. These lesion maps tend to be smooth, so an effect you see in one voxel is not necessarily driven by the data in that voxel. It could be driven by correlations elsewhere. So I guess what I would say is that it's important to use a comparison that makes you feel sort of comfortable with what you're testing, and at the same time to sort of be aware of the sort of family of alternative hypotheses when you see results. And this goes back a lot to these sort of patterns of correlation between voxels. You can see these artifactual correlations between fairly distant voxels. I shouldn't say artifactual. These just correlations between the lesion patterns and different voxels for various reasons. One might be that some set of patients has unusually large lesion drawings because they were all CT patients or something, or some set of patients happens to have damage at an area that required, due to the sort of vascular origin, created damage, was also responsible for damage to another area. So it's certainly worth considering the space of possible hypotheses. That said, if you see damage in this posterior voxel in the left hemisphere, and not an anterior voxel in the left hemisphere, in an analysis where you've included right hemisphere patients, at least you can say numerically or informally that it could be driven by left hemisphere, right hemisphere effects, but there does still seem to be something special about that voxel within the left hemisphere. Now, that observation comes down to something else that's on this list, which is this issue of spatially discriminating inferences. I guess I shouldn't click on it. Which is really, I would say, if any sort of grave warning could be given to everyone who's going to